As a definition of regime condition, we can state like that: alluvial channel carrying a certain discharge, and that part is very important, that when we are talking that this channel is in regime condition, we are always talking about that it is in a regime condition for this particular discharge. That is very important. So it is carrying a certain discharge. Alluvial channel carrying a certain discharge undergoes changes in bed width, depth, and slope. Of course, in when I was saying, I was not mentioning about the slope. The slope will also get adjusted when the charge is, when the velocity is more, it will be eroding, and slope may that way get increased. When the charge is for that particular discharge, when velocity is less, sedimentation will be there, and if the sedimentation start from downstream, then discharge slope can reduce. Of course, if the sedimentation take place at the upstream itself and downstream is, so all sediments are getting deposited at the upstream, then when all sediments are depositing at the upstream and downstream is getting free of sediment, then again that water may start eroding, and that way slope can increase also. So that way this change of slope will continue. So this slope is also getting adjusted, and until an equilibrium is reached. So finally it will reach an equilibrium, until an equilibrium is reached, and become a stable channel. And that stable channel is called, that channel is in regime condition. Well, and for using Lacy's theory, or say before going to Lacy's theory, some of the term we should have very clear idea. That is, we say that the Lacy's principle will give us one channel which will be in regime condition. But what is regime condition? We have explained. But then we should know what is true regime condition. So understanding following terms are important. That is, first let us see what we mean by true regime condition. Because many a time we say that this is in regime condition, but true regime conditions are very special. And of course, we must know that in practical field, getting a true regime condition is very difficult. But still, we go with that assumption. Now, for true regime condition, discharge is constant. Now, if we think about a natural channel, then definitely for a region like India, where our rainfall is fluctuating a lot, I mean, seasonal variation of rainfall is quite high. And there, we cannot imagine of having a fixed discharge through any natural channel. So though we see that this channel is in regime condition many a time, but it is not exactly true. Of course, there we find that for the dominant discharge, this can be considered to be in regime condition. But when discharge increases, again a channel may get eroded, and again that there may be deposition in the channel. And that's why for the river of India, where the rainfall is more, suppose rainfall is more in the again northeastern part of India, if we talk about where rainfall is very high, then in those areas the discharge is fluctuating a lot, and that's why the channel to have a perfect regime condition is not possible. It always keep on changing, and that's why we are getting braided channel, then channel meandering is taking place, channel, because at some point the sediment get deposited at certain point, and in other part it is getting, and in another season it is getting eroded. So that sort of things keeps on going. But when we talk about man-made channel, because when we are talking about design of channel, we are basically talking about man-made channel. Then suppose man-made channel means it can be irrigation canal. If it is a irrigation canal, then of course we can think to some extent about a constant discharge. If we feel that for the irrigation we'll be supplying a constant discharge. But again, here also that point comes. Because if our agricultural field is in a region like India, this will require irrigation only when it is not raining or when the crop is facing water stress. So we are not always allowing the same amount of water to the canal. Because again, if it is controlled by a reservoir on upstream, we need to store water when the rain is coming, and then we need to release water when there is a lean period. And that's why we cannot afford to have constant discharge. But still, there can be the variation we can minimize, and we can think of having some constant discharge. And of course, if the canal that we are designing is a drainage canal of a city, then definitely this condition cannot be satisfied. But still, we need to design with some assumption in this part, with some discharge considering as the dominant discharge. Then, next point is that means for true regime condition, this must be satisfied, the first point. Then silt grade and silt charge are constant. Well, what we mean by silt grade and silt charge. Silt grade means the size and distribution of the silt size, rather. Say sometimes we call well graded silt, sometimes we call poorly graded silt or uniformly graded silt. Means poorly, if in a silt portion, if we find that all silt are of uniform size, then it is uniformly graded silt. And when it is uniformly graded silt, means all are of almost uniform size, this is not good, rather it is bad. Because if we have say smaller size, bigger size, then all will get, say smaller size particle will go inside the bigger size particle, like that. Say these are bigger size, and then these are suppose some smaller size. So this smaller size will go inside, and then the interlocking will be better. So, but if it is a poorly graded, that's why if it is a uniformly graded, all are of the same size, then there will be lot of gap in between, and that's why these are called poorly graded. So, and well graded means when there are smaller and bigger mixed different size. So like that, this is basically the gradation of the silt, we call like that. But to represent this, we need a value. So generally, the average particle size is given to use the gradation. And in this case, of course, when we talk about grade, our emphasis is to see that whether if the silt are of bigger size, then it will not be eroded easily. If they are of smaller size, it will be eroded easily. Of course, if it become very fine, then of course it is not coming under alluvial formation. Then if it become clay, that is not erodable. That is a different thing. Its adhesive property or its cohesive property is very strong, and that creates some other sort of bonding. But when we are talking about alluvial formation, then if the silt is of finer size, it will be eroded quickly. And so the average size of the particle is significant. And that's why this by silt grade, we mean that what is the size of the silt. And that can be represented as D50, means that if we use sieve analysis, and then suppose we are sieving the entire silt, and then we are finding that how much percentage of the silt is passing through the, 50% of this is finer than that say particular size, and then that we refer as, that particular size we refer as D50. That is 50% of the silt will be finer than that particular size. When 50% is finer, definitely 50% will be coarser than that. So that particular definition we use for representing the silt size. And then what is silt surge? Well, silt surge means the volume of silt that is coming into this channel. And then suppose not only the size of the particle, what is the total silt concentration, sediment concentration in the water. So sediment concentration which is flowing means it can be in the suspended form, it may be moving through the bed. So how much total sediment over the bed, as we were discussing that part earlier also, that is the bed load and suspended load. So that way, what is our, say when we were discussing mobile boundary channel, I recall. So when we were discussing mobile boundary channel, then this part we were discussing uniform flow in mobile boundary channel. So in that case, we were discussing that sediment can be moving along the bed by jumping or rolling, or it can move in getting mixed up with the water. So entire things, total concentration of bed load and suspended load we call as a silt charge. So how much silt charge is coming, that is important. But the point is that in Kennedy's theory or in Lacey's theory, we are not using any parameter to take care of this silt charge. We are just considering that it will be in regime condition, that when silt charge that is flowing through the channel and the silt grade is constant. Well, then next point, this is more important, that flow occurs in an incoherent alluvium. That is, cohesiveness is less, incoherent alluvial, that is, it is a alluvial soil, incoherent alluvial of unlimited extent, carrying silt grade same as that of the formation. So this sentence, what it means, that for true regime condition, to have true regime condition, our channel should be of infinite extent. That means infinite extent of incoherent alluvium is there, and through that our channel is moving. And then it is carrying silt grade same as that of the formation. So in the bed through which the channel is going, the suppose through a particular alluvium the channel is moving, so the sediment size of the alluvium, silt size of that alluvium, we will be getting some value. If we take some sample and if we see what is the D50 of that we are getting there. And then what sediment it is coming from upstream, that is coming from far upstream, and that is coming as silt charge. And in that silt charge, the value what we are getting, the dimension or D50 of that what we are getting, there, okay, D50 may not be the index, we can use some other index also in case, but whatever index we use, the size of or the grade of silt charge that is coming from the upstream and the grade of silt charge that is remaining in the bed, this must be same, and that entire alluvium should be of infinite extent, and then only we can have true regime condition. Now, when we go into these 3 points and when we think about these 3 points, then one point is very clear that when we are talking about application of Lacey's theory, then we know that true regime condition, if it is to be achieved, then it is very difficult in the field. And that way, there will be definitely some error in the design or limitation of the design. Well, then some other important point when we are talking about artificial channel, that artificial channel, there are 2 stages of regime. Well, we are now till this point, we are talking about regime condition, and we are talking about true regime condition. What are the conditions that we should have? But in artificial channel, when we are making an artificial channel, then there are 2 stages of regime. So this is called 2 stages of regime. One is called initial regime and the other is called final regime. And of course, some more points are there that we need to know, but still, as a beginner, we should know that what we mean by initial regime, when only depth and slope has undergone adjustment. So initially, when water will be flowing through a channel, then the depth of the channel and the width of the channel, finally the width will also get adjusted, but initially the depth of the channel will be adjusted. Means if the velocity is high, it will be scouring in the depth, in the depth-wise direction, so depth will be adjusted, and the slope of the bed will also be adjusted. Well, so initially the depth and slope get adjusted, and when these 2 are getting adjusted, and we are getting more or less a stable channel for some intermediate period, and this is called initial regime condition. And then, of course, after some time, it will start eroding from the side. And then its width will start increasing, or if it may get decreased also if deposition start, means width will start adjusting. So when both, when this 3 parameter, that is depth, slope and width, gets finally adjusted, then this is called final regime condition. So once we get initial regime, then we call this as a final regime condition when width has also undergone adjustment. And in the entire process, the side slope is also getting adjusted. Side slope is also getting adjusted. When we are talking about a regime condition, we say that side slope will have its own value based on the erosion and deposition. So that way, we are not providing a side slope directly here. That we will assume that for the regime channel, this is the side slope. Of course, in Kennedy's theory, we were not talking about the side slope, and based on the sediment characteristic, we can have some side slope there. But here, we are saying that in Lacey's theory, side slope will get adjusted. In fact, he suggested some value for the side slope, or from observation, it can be taken that side slope can be taken as 0.5:1. That is for one depth, 0.5 width. So that way, the side slope can be considered. But one more important point that I am putting in red here is, you can concentrate on the slide, that it is not necessary that to reach the final regime, the channel will have to pass through initial regime. So the channel need not pass through initial regime to reach the final regime in all cases. Normally, of course, it goes first to initial regime, then it achieves its final regime. But sometimes, without passing through the initial regime, it can reach its final regime. For example, suppose final regime width of the channel should be, say, 5 meter, for example, and we have made a 6 meter wide channel, and then the flow is flowing through that. So what will happen? The depth wise it is adjusting, and then width is also getting deposited. Channel sediment that is carried by the channel may be depositing on the side because width is larger, and that way, by depositing, finally it is coming to the width of 5 meter, which should be in the regime condition, and that way we may get a regime channel without passing through the initial adjustment of only bed and slope. So that way, this is not the necessary criteria. And then more importantly, Lesy's theory, what he studied, and based on his study, what are the formula he has given. Those are applicable for final regime condition. So once we are designing a channel, we should know that this channel we are basically designing considering that this is the final regime size. And so those formula will be giving us this value. Well, then he gave series of formula. Initially, of course, he gave 4 formula. These are the 4 formula that were given by Lesy. First is that this is not exactly a formula that it was found, or it was rather observed in many cases, that side slope, it can be considered as 0.5:1 for when we are designing by Lesy's formula. The side slope we can put like that. And of course, the next formula, or the other, this 4 formula what he gave, is that unlike Kennedy's formula where the silt factor was not given at all importance, later on only they introduced a term called M, the critical velocity ratio, which was used to take care about the silt factor. But unlike that, Lesy first gave the formula for silt factor. Silt factor F, he gave this formula as 1.76 root over MR, where this MR, that is, which is basically representing the particle size, and that MR is considered as D50. So for the design of Lesy's channel, or Lesy's theory, application of Lesy's theory, if we go to the field, first we should collect the sample through which the channel will be made. Then after collecting the sample, we should carry out sieve analysis. And then after carrying this sieve analysis, then we should see that the size of the sieve through which 50% finer we are getting, that we should consider as the D50. And that D50 value we should put here, and then that we should consider as a representative value of silt factor F. Otherwise, silt will be of different size definitely, and we need a definite value. So that definite value we are getting by this approach. Well, then we should calculate the mean velocity. And then he gave some relationship between, in fact, he gave 4 relationships. One relationship is between the mean velocity V and this R. R is nothing but hydraulic radius. And that is what this A by P. R is equal to A by P. Well, we know that in Manning's formula, or in our uniform flow formula also, we relate this velocity to the hydraulic radius R, and then we take care of the slope. But here, this is the velocity which we try to achieve, and then this velocity is equal to, is given as 2 by 5, rather root over 2 by 5 FR. Again, silt factor is playing a role here. And in fact, in all those formula, in most of the formula that he has given, the silt factor has a vital role. So the determination of the silt factor is very important. Well, and then the V, we can have 2 by 5 F into R to the power half. So that relation he gave. Then he gave another relation. So here also one relation for V, and another relation he gave between the area, that is the cross-sectional area of flow, and the velocity V. Cross-sectional area of flow and the velocity V. So between this velocity V and cross-sectional area A, he again gave this relationship that A and F square, again the silt factor is coming here, is equal to 140 into V to the power 5. 140 into V to the power 5. Well, Now say this, you can see very well, just okay, I'll show you later. This is one relationship. Then say another relationship he gave, that is the flow equation. Normally in Kennedy's formula or in our design of uniform flow channel also, we were using the say uniform flow equation, that is V is equal to say 1 by n r to the power 2 by 3 and s to the power half. This is the Manning's formula. And there we took that n value that can take different value based on the material. And when we are going into the field and we are seeing the material, then what will be the n value? Taking a decision about that is very difficult, of course. Yeah, unless we have a lot of experience on seeing different type of material and then experiencing how the depth of flow will be, or whether the depth of flow, the uniform flow depth we can have by using a particular numerical value for this n. But here in Less's formula, rather than giving 1 by n, the other part is remaining same, say r to the power 2 by 3, s to the power half. This part is remaining same as the Manning's formula. But he gave a value 10.8. 10.8. By experimenting, by collecting data from different sources, from several portions he collected data, several table section he observed and collected data, and he gave this formula that the velocity can be computed by using this direct formula, where we did not be worried for the n value. Rather, we can take a definite value of 10.8. So that way, when we try to compute this, computation become easy. But of course, the limitations, those are there, as we are considering a definite value, that is having definitely some limitation. And of course, this formula was not given directly, but still for freeboard in Less's formula, we can use this relation. It is actually not for the channel design, but what he gave, that if the channel need to carry higher discharge, freeboard means, say if we have a channel like this, then say by design we are getting that this much is the depth D, and this is the width B. So we have got this design. But the channel, when we are putting in field, we cannot put exactly equal to D, because due to many reasons, this depth can increase beyond that. Or maybe the wave are coming through this channel, and that way also it can exceed this limit. So always it is necessary to provide a freeboard. So the channel we are constructing to this much. Our water depth is here, but we are always providing a freeboard. And he suggested that this freeboard should be more when discharge is more. And that way, he gave a relationship that is 0.2 plus 0.5 q to the power 1 by 3. So that relationship was given by him. And now just we want to discuss about this formula, another aspect, that is AF square is equal to, suppose, 140 V to the power 5. See, this formula, if we multiply by V, then what we will be getting? Suppose if we multiply by V, then what, multiplied by V, right, multiplied by V, then it will become area into velocity. And from the continuity condition, we know that continuity relation, we know that area into velocity is nothing but Q. And for design of channel, always, well, in all this formula, we are not talking about Q except the freeboard. But in all this formula, we are not talking about Q. But channel, we need to design for a given discharge, And as such, we should be careful about, or we should be concerned about what the Q value is. So you can concentrate on the slide that if we write here Q, just multiplying by V, this formula will become Q F square, and this is equal to 140 and V to the power 6. Now, from this relation, just by multiplying V, we can have another equation, which is relating Q and V. So now we can write as V is equal to, say, q f square by 140 to the power 1 by 6. So that way we can write v is equal to say q f square by 140 into 1 by 6. So this way, that means from one formula, suppose we want to say q is given, then say in practical field, as I have already explained, that taking the silt data we can find the f. Our target is to design the channel for a particular discharge. So this q is obtained, f is known, the q is our required things, it is given, f we have obtained. Then we can find what should be the velocity, then this v we can find out q f square by 140 to the power 16. So this equation can be manipulated to have different relationship. And then we can try to see if this v is to be achieved, and say v is equal to, from this formula we can see what will be the relationship between a and b. Between v and y, because r is a function of b and y. From here we are getting some value, okay? And then here we are, or we can go by other way also. So here it is r, and if we put r here, again slope term is here, and what will be the slope we should take, or say once we get the v value, then we can go back to this formula. Say first formula, this one. In this formula, as we have got the v, we put the v here. By putting the v here, we can get what the value of r is, because f is already known. Getting that r, we can now put here r, and we can get what slope should be, or that way we can indirectly calculate the advisable slope in that channel. In fact, in some channel, suppose of course we say that natural terrain will govern the flow, but we have a scope of adjusting the slope also in some case. Suppose our terrain is having a particular slope, but if we try to increase the slope, we can align the slope in a curvilinear way like this, and then we can have a slope, a different slope. So like that we can adjust it to some extent. So what I want to emphasize from this point, that by manipulating these equations, we can have some derived equation which were perhaps were not given by lessee, but we can derive some relation from these equation itself. And one of those equations are, some of those equations are very important, and we can directly use. One is the perimeter P. So as I have already explained, that we can have from here, say we are getting Q, and then perimeter is equal to, say, R is equal to area by perimeter that we are getting, and area we can calculate from this continuity equation, also knowing the V, and putting those value we can then indirectly calculate P also. So P in terms of Q we can calculate, and that formula is 4.75 root over Q. Well, so if Q is given, or Q is our required things, from there we can calculate the perimeter, and this perimeter in many a time is used for considering, suppose in a breeze we are considering and we want to reduce the waterway because the breeze will be smaller than the actual width of the river. We narrow down the breeze portion for economic purpose. Then P will indicate what should be the minimum width of the breeze. Otherwise our perimeter will further reduce, and then it will not be in a regime condition in nature. So to have the channel in a regime condition, or to not to violate the regime condition in a much way, this P is used for that purpose also, finding the minimum say waterway in breeze, and different purpose also used. Similarly, the score depth, this is also used for design of many hydraulic structure, that what will be the R. That R means we are calculating by indirectly from this formula, that is QF, and these are coming. This is in terms of total discharge, this is in terms of unit discharge. And by using these things we are getting R, because this is in regime condition. This will be, suppose in a channel we are having this much of depth, but we know that it will get eroded and then it will be depositing. It may deposit or it may erode. If the depth is less, suppose it will be flowing in this depth, then suppose its regime condition depth is much higher, then it will be eroding, and the ultimate depth may come up to this portion. And then if we are constructing a hydraulic structure here, then if this water eroded up to this much depth, this hydraulic structure will not remain, it will be washed away. So we'll have to provide some provision, say we are putting some barrier here, so that This erosion, even if it comes to this much of depth, it will not take this hydraulic structure away, and this is called cut-off sort of things. And for designing those things, we use this score depth. That's why it is called scour depth, because this is the depth in regime condition. And of course, this is the normal scour depth, but in again, depending on some other criteria, if there is band, if it is straight, then we need to, for design purpose, we need to take some safeguard, so we get the actual score depth, we can multiply it by some factor. And similarly, bed slope we can calculate using this friction factor, silt factor, and this discharge. And of course, by two different ways, if we calculate, we get two different formula. And these two different formula will of course not give identical value. One is relating R, one is relating Q, but both the way we can go, and it will give us some tentative value for this Q, for this bed slope. So all these formula we can apply for design of channel by using Less's formula. Well, and as discussed, there are some limitation, and practical knowledge of the practical field of a particular region is very important. We apply this equation in a more confident way. Then some other methods are there, as we explained, it's attractive force method, and those we'll be discussing in our next class. Thank you very much.